Welcome to episode 2 with Science Unboxed with Professor Matt W. I want to go over what we went over last time to kind of make a summary of what we did for quantum mechanics. We were at explaining the end of Newtonian physics. In the 19th century, we explained that Newtonian physics was completely at a standstill. Atoms shouldn't exist. Ultraviolet radiation that we give off, human beings, animals, anything, the sun, it should have an infinite amount of energy. In addition, different elements seem to have different colors. They emit different colors. And finally, we didn't have an explanation for the photoelectric effect being affected by color. Now, Einstein was able to prove that light comes in these particulates called photons. What captures all these two things are two keywords, or one keyword and one key constant. The keyword is quantum or quanta, meaning quantity. There is a discreteness about the universe. The universe is discrete. There is no infinite. There is no zero. Okay? There's a discrete amount of energy things can have, and there isn't an infinite amount of energy or infinite amount of velocity things can have. So the speed of light for a long time was thought to be infinite. Well, it's not. There's a number to that, right? There's a speed limit that even light can go. And for a long time, we thought that there's a discreteness, that we could have zero energy levels for things like atoms. Our pioneers were Einstein, first showing that there is a discreteness to light. It's not just a wave. There's particulateness, discreteness to light, and we call those things photons. Niels Bohr showed that the angular momentum, that is the electrons that orbit a nucleus of an atom, have a discrete orbital that they have to fill, that it can't be right next to the nucleus. There's a discrete lowest energy level, and it is not zero. And all of these things have in common, in addition, there is most likely also a discreteness to the dimensionality of the universe. We'll get into that in string theory and gauge symmetry. But what these things have in common is this quantity, that things have a discreteness, they have a number quantity. And that number might not be integer in number, meaning 1, 2, 3, 4, 5, 6, but it does fall in some type of pattern. That's number one. Number two is Planck's constant. None of this would be without Max Planck, the physicist who was saying that basically there is a discreteness to the universe, especially with ultraviolet light, and there's a minimum energy that allowed his equations to exist, so that there wasn't an infinite amount of energy emitted from black body radiation. All right. So Planck's constant is going to come up. And that Planck's constant isn't a fudge fact. Isn't necessarily something that was experimentally determined. It was a fudge factor that needed to go in. Now, it came up experimentally, but it had to be put into the equations for the equations to work and not have this catastrophe. So now that we have the help of Einstein, we have the help of Max Planck, we're able to move past this. But by moving past it, we move into a new world. It's not the same world as Newton anymore. There is a discreteness to the universe. There's no such thing as zero. There's no such thing as infinity. All right. Things can't have infinite velocity. Things can't have zero or completely zero energy. We are in a new world of physics. But I think there's some fundamental aspects we have to get to first before we go on to that. And we will work up to that, because that requires some idea about things like the Standard Model, what an electron is, for example, and what its buddies are, such as the neutrino or other leptons, and then also an explanation of quarks, those things that make up neutrons and protons. So I think it's more important to understand the basics of where we are with quantum mechanics. So realistically, we have to go back to just what is an electron. Okay, so an electron is a particle, at least we think so. At this point, we're going to prove that it is both wave and particle, and then eventually probably drop the particulate idea altogether as the paradigm shift completely emerges and we're left with no such things as particles. But for right now, electrons are an indivisible type of particle. We'll call them indivisible particle. So how is that different from a proton, you might ask? And if you have no background knowledge, the atom is composed of neutrons and protons in the nucleus, and then electrons orbiting that nucleus at different orbitals. And that has to do with the angular momentum of the electron. So an electron can't be broken down anymore. All right. That is the smallest subunit of that type of particle. However, the proton and the neutron can be broken up into things called quarks. And quarks, for every neutron or proton, there are 3 quarks. And to hold together these protons and neutrons, you don't just need the actual quarks, you also need a force carrier. And that force keeping the quarks together is called gluons. They're mostly gluons, and they do exactly what they sound like. They glue those particles together. And again, I use the word particle when I should be using the word wave, because we've come to realize things are waves, but we'll go over that later, how we make this jump, and that's what this lecture is about. We're going to go over how electrons, we move from the idea of it being a particle to both a wave and a particle, and then future lectures will show that how it's pretty much a wave in general. So a proton is composed of 2 up quarks and 1 down quark, and a neutron is composed of 2 down quarks and an up quark. All right. And they're glued together by these things called gluons, and they are the force carriers. It's what connects those particles. Now, for the electron, force carrier of the electron is the photon. So that's why the photon and the electron are related. But all of these will be related. We will be able to get all kinds of different particles out of collisions once we talk about synchrotrons and cyclotrons. But for now, I just wanted to briefly explain a rudimentary knowledge of what an electron is, a proton, and a neutron, what an atom is. We have this thing, an atom. We have this thing called an atom, also an element, and you have these electrons that are orbiting it. All right, so what does that do for us? Well, light interacts with electrons via the photoelectric effect, like we talked about with Albert Einstein, and we have these photons now. And what we have to think about now is it was always viewed that, well, it was viewed for many centuries that light was a wave. Einstein says, wait a second, it's a particle. So we need to take a step back now and talk about what a wave is. Again, a wave is some type of movement of energy, and it has a wavelength. That is the length between one amplitude and another, or one note and another, and we use the Greek letter lambda to denote that. The amplitude of the wave is how high that wavelength is. And as I've suggested before, all a particle is, realistically, is the highest amplitude on that wave. So that's what we see as particles. Anyway, so we have the particle, which is designated by the Greek letter lambda. We also have the velocity. That's the propagation of the wave. So that's how fast the wave is moving. Now, of course, with light, that's going to be c, and the velocity isn't going to change. So we can't change that. But we also have this thing called frequency, and that's how many times it passes per second or pulses across you. How many passes the wave comes to you per second. So if we're thinking about a water wave, how many of those water waves pass you per second? That's the frequency, and that's denoted by f. Now the period, and that's how long the wavelength takes to pass us, a measure of time. So that's the inverse of the frequency. So 1 over f will equal t, the period. And so we have this equation: velocity equals the frequency times the wavelength in a wave. Okay, so that's what a wave is. We see a wave in a lot of different types of situations. We're going to go over how a wave works with water. That's the easiest thing to think about. Think about how waves work in your everyday life, where you see waves. You might have a cup of coffee and your table moves, and suddenly you see waves in your cup, water waves. All right. And you might see the source of that propagation and how many kind of come by in a certain period of time. That's one way we see waves in our everyday life. Another type of wave we might see is a sound wave. Sound waves, of course, they are what allow us to hear. And so we're always going to be thinking of sound waves too. Different type. They're a compression wave, but nonetheless, they're a wave. They're a matter wave. We're also going to have to think about where we see particles. I mean, we see particles everywhere. So anything that's solid is a particle. But a good way of thinking about it is a ball, maybe a tennis ball, maybe a bowling ball. But whatever we think of, that's going to be our particle. So we want to see how an electron, which I just told you is a particle, but also a wave, how is that? How does that work? How would you develop an experiment to really figure that out? Well, most of them early on were thought experiments by Richard Feynman, and most of them had to do with slits in a wall. So imagine you have a wall, all right, and you might have one slit in the wall. We'll first do particles. We'll first do tennis balls. So we have a wall, and then we have strike paper or another wall behind it that will kind of like, it will record where the tennis ball hit the back wall. So there's a slit through the first wall, and then the back wall doesn't have any slits. It's just recording where it hit. So might call that strike paper, or you could think of it as having ink on it or something like that, or the ball's originally having ink and it hitting the wall and leaving a trace. Okay, so imagine what would happen if I threw 1,000 tennis balls at that one slit. Okay, in that first wall. So I'm throwing 1,000 tennis balls. What do you think would happen? And you might say, well, what would happen is most of those balls would go through the first slit. Some might ricochet in different directions, but most of them would be right behind the slit. So the majority of those balls you would see on the second wall, the strike paper, as being behind the slit. So you would see it kind of like almost like a line, right? Now let's repeat this experiment. Let's do it on a different part of the wall. So instead of doing it on the right side of the wall where we have a slit, let's think of it doing it on the same idea. We have a slit on the left side of the wall, still just one slit. We do the same thing. We throw the tennis balls through the slit, and it hits. It does exactly the same thing. It hits, goes through. Some might ricochet, but you get a general pattern, a general line behind the slit of the first wall. It's hitting the second wall, right? So we see kind of the same pattern. Now let's do another experiment. Let's open both slits. Okay, so we'll have the slit on the left and the slit on the right. And when I say slit, I mean hole. You could just think of a hole, like a rectangular hole is the best way to think about it, on a wall. So I'm going to push tennis balls through the first one and the second one. And what's going to happen is exactly the same thing. It's going to behave the same way as the first experiment and the second experiment. You're just going to see a line on the left and a line on the right. That makes sense, right? That makes some sense. That's how we kind of see the world. Would we expect to see the same thing with a water wave, though? So imagine if we're now looking kind of down on the walls. We still have the two walls. We'll have two walls. The first wall we'll start with one slit. The second wall will be the strike paper or some way of recording where the wave hits the second wall. And we'll fill it up with water. We'll fill up the space in between with water. So we'll create a propagation wave or just a water wave, like you see at a park, like a water park that has a wave tank, and we create the wave. Goes through the first slit. Well, what happens? Well, what we'll see on the other side when it goes through the slit, we'll kind of see like a pattern, right? Because the wave will go through the slit and then still propagate and create kind of a pattern of where there's a high amplitude or just a high region and a low region. So we'll get like this almost bell curve, right, of where it's hit. Okay, so that's what happens with one slit. Now let's think about what would happen with a slit again on the other side. What would happen? It would be similar. The bell pattern would move, but we'd still have a bell pattern from the first wall on the second wall. 1 second. So take this part out. So we would see air in this experiment with the one slit and the water waves. We would see high areas and low areas, and this would eventually turn into that bell curve that I was talking about if you were to do a time-lapse video and you're able to take away all the interference. Okay, but what happens when we create two slits? Okay, well, so I'm going to have a slit on the right, and I'm going to have a slit on the left. I'm going to have a propagation wave of water, so I'm going to push that wave out. The wave is going to hit this slit and then move into the second wall where it can record. And we're going to have these interference patterns, right? Because some waves will cancel out other waves. A high wave plus a high wave is going to make the amplitude is going to be higher. If we have two inverted waves, if we have a node and a high amplitude, is going to cancel out the wave. So we're going to have this interference pattern that hits, right? And so we're going to have this strange kind of pattern that isn't necessarily a bell curve. It's going to have a high amplitude in the middle, and it's going to have some other waves, but lower and lower until it gets flat on each side. So we would have high amplitude, and then maybe a node, and then we'd have another high amplitude, but not as high as the original, and then it would keep on leveling out and going down in each direction. So we would have this kind of up and down motion. It would be big amplitude, nothing. Then an amplitude, like maybe, let's say 3/4 amplitude of the first, then nothing. Then a quarter amplitude of the first, saying the height of the wave, then nothing. So we get this kind of like pattern that you'd see in a sine wave, right? That's getting smaller and smaller. The point is, at the ends will be completely flat. So the ends will have no amplitude. Okay, and so what's the connection to the electron? Well, now let's send electrons through. Okay, so we have the two walls. We have the first wall and the second wall. We have a slit. So we're going to send electrons through the first slit. And what happens? Well, what happens with the first pattern is that we get the tennis ball pattern. So when there's one slit, we're going to get a tennis ball pattern. We're going to get a line of where the electrons went through. All right, so okay, it's a particle. Electron, we knew it was a particle. We just proved it was a particle. Okay, now let's try it with two slits. And this is where it gets strange, all right? Now, when we have two slits in the first wall, what's going to happen is it's going to appear like the water wave. We're going to have these areas of a lot of electrons and then no electrons. We're going to have an interference pattern with the highest amplitude in the middle. Okay, so the most electrons will have gone through the middle, will be in the middle, and then the least electrons, there'll be less and less until it's flat on the sides, just like the water wave when we had two slits. All right, so that's very strange. The electron is somewhat schizophrenic. It's acting like a particle when we have one slit, and then it's acting like a wave when we have two slits. So there were further experiments that tried to figure this out. And one way you could think of is, well, let me see where the electron actually went. I need to know which electron went through which slit. And so how you would do that is maybe you would have light behind the slits and some type of way to capture a photograph. But when you do that, when you actually try to record it, what happens is you get a particle. You get the tennis ball pattern through both slits. You don't get the wave pattern, okay? Well, let me turn off my recording device. Well, if I turn off my recording device and then see how it goes at the end, but how it appears on the wall, then that interference pattern will emerge again. So that's very strange. So if I record and try to detect which electron went through which slit, I can't do that. There's no way for me to do that because then it turns into the particle, or it more precisely behaves like a particle. I can't actually figure out which electron went through which slit without changing the nature of the experiment and changing the nature of electrons. So right now, we have an electron acting as both wave and a particle. I hope that breaks down how that works, all right? So you can do this experiment with electrons. You can also do it with other sources like light, especially if you have you have a photon emitter where we can detect a laser, which is a very focused form of light. Very important distinction. And so this is where we really need to start thinking about the world differently. The world now is dependent on whether or not we record it. So that brings up so many philosophical questions of bias, of subjectivity. How does a scientist know where an electron is? And can they know where it is? And it still behave like a wave or behave in its true nature. A lot of philosophical ideas arise from this problem and this duality. We call this the wave-particle duality, of electrons. Now, like I said before, we're going to eventually learn that this is true, and it even pushes back toward the wave theory that the particle, the electron, what we perceive as an electron, what we perceive as solid matter, is actually the highest amplitude of that wave function. That if a wave was sitting on a couch or a wave was a couch, for that couch to exist, it has to be in its highest amplitude state, or I would fall through the couch. And this goes back to the idea that most of the world, most of everything is empty space. And it's only when the waves go through empty space and have high amplitudes that we do see this particleness to the world. So it's a very interesting way a new way to view the world. And it also throws out a lot of ways where we can record the world. So, like I said, subjectivity is going to be a huge factor. How to make sure that the electron is where we say it is, or is that even a valid question anymore? And it isn't. It's not a valid question to ask. If I shoot electrons out to know where a specific electron is at a certain time, we can't ask that anymore. It's a world of probability and statistics. And what you'll find is another theme at the end of the 19th century, emerging in the 20th century, is this new kind of area of mathematics called statistics. And statistics was applied to all the sciences. It eventually becomes the most important aspect of the scientific method. Without it, you can't really have the scientific method anymore in modern science. But statistics was applied to all of these fields. It was applied to biology, geology, all the natural sciences, physics, chemistry. And the world starts working in terms of probability rather than certainty. That clockwork universe of Newton and even Einstein. Einstein is going to continue to state, and he's going to continue to try and prove that there's a certainty to the universe, and not a probabilistic aspect to the universe that quantum theory suggests. So it's a new way of looking at the universe, that there is no certainty, there's just probability. I can only find the electron in certain areas. I only know that the majority of the electrons will be in one area versus another area. And this will be true of all the particles, or what we call particles and light. But this was, like I said, this was applied to geology, statistics. Evolutionary theory is really applied statistics. Genetics, for example, is completely applied statistics. Genetic theory is realistically just applied statistics. Mendel's crossbreeding of pea plants was applied statistics. He had a mathematical ideology of what he was trying to figure out based on probability, which is in statistics, in the realm of statistics. And he proved that for years before we had anything like genes or DNA. Remember, we didn't know that DNA existed. We didn't know that genes existed in biology. We just knew that there were these patterns. And you could go back in human history. We've been domesticating plants and animals, and that's really what started civilization, is domestication of plants, for the last 10,000 years or more. So applied statistics, trumps and is really the precursor of genetics. And then you get into evolutionary theory and how things change. It's a statistical likelihood. It's, yes, there's other aspects like survival of the fittest and so on and so forth, but ultimately it comes down to the statistics, the probability of a certain species surviving versus another based on its genes and how good they are for the environment. And those genes, the whole idea of genetics is applied statistics. And chemistry eventually becomes, chemical reactions are applied. Statistics are applied to chemical reactions. We have a certain amount that is created, a certain efficiency of an experiment, of how many molecules are created of, let's say, if we're combining some type of sodium metal and water, creating sodium hydroxide, what is the efficiency of that experiment? So again, applied statistics to chemistry. And in a way, quantum physics is applied statistics to physics. And when you do that to physics, which is the foundation of all sciences, it is the hardest science there is, it starts to unravel everything else. It puts everything else on shaky footing. And what I mean by that is, when I say it's the hardest of the sciences, it's that we'll start with psychology. Psychology its theories are very hard to prove with physical evidence, right? That's why it's psychology, not neurology. So psychology is based on biology, based on the brain, or at least now it is. It's based on the brain. Some people would correct me on this and say, nature versus nurture. But the idea is if psychology is a science and it is a physical reality, then it's based on biology, it's based on neurology, it's based on the brain. Biology is based on chemistry. Biology, in terms of our organs and how we function as organisms, are dependent on chemical reactions. Chemical reactions, of course, are based on physics, fundamental laws of physics, such as Pivner. Pressure times volume equals the amount of moles times constant times temperature. And we can go back and forth through this. But the whole foundation of all physics, now we're talking about electrons and atoms and molecules. We're not even talking about molecules. We're talking about things that make up the universe. These are the things that make up everything else. And we can't say with certainty where they are. And start thinking about that as a concept. You can't say where it is. You can just say a probability of where something is. I can't tell you where an electron is. I can tell you a probability of where it is in an electron cloud. When I say cloud, I mean that the cloud is literally a probabilistic model of where the electron could be around the nucleus of an atom. So I can't tell you that, where it specifically is. And this experiment, these thought experiments, and eventually we create actual experiments to prove this. And it's interesting. You can do these experiments at home, and now there are ways to do these experiments. But originally they were thought experiments, and they're very simple, and eventually were proven correct. So the last thing I want to comment on is there were a lot of holdouts about quantum mechanics, especially in the United States, especially in other areas of Europe, and also as Nazi Germany was becoming more powerful and the anti-Jewish sentiment, anti-Einstein sentiment started gaining traction. There were a lot of critics. People devoted their whole lives to criticizing quantum theory. And the last real experiment that basically the home run is the Compton effect. And the Compton effect, which was constructed in 1923, showed what happens when light, in this case X-rays, interacts with electrons. And historically, the Compton effect was, for many old-time physicists, the final convincing evidence. Classical physics predicts that the electron should absorb energy from the light wave, then remit the same frequency. However, the experimental evidence shows that the light scatters off the electron with a lower frequency, almost like it hit it, like a billiard ball, and then comes off with less energy, like momentum. And incoming photon bounces off an electron, giving up some of its energy and lowering its frequency with the equation equals HF. So the Compton effect was proven in 1923, and that anyone that doubted quantum physics and the idea of the atom behaving in this way, in terms of electron orbitals, discrete orbitals of angular momentum, they kind of quieted down. Now, people still did not accept it. Einstein did not accept it, even though he started the wave. He is responsible for opening the door to the quantum world. And he didn't exactly like the uncertainty that some people took the theory to the extreme. And he had many, many papers with Niels Bohr and public appearances with Niels Bohr where they would debate, and we'll go into more of those debates next time and the final experiment that kind of disproves Einstein. Follow me at Professor Matt on all social media, and stay curious. Hopefully you learned something, and this made quantum physics a little bit easier to understand. Thanks.